you all in this class. This is the third lecture on heat and heat and mass transfer, and we are covering unit 1. And in this class we will be dealing with heat conduction equation. Till now we have discussed about the basics of basics of heat transfer, where we discuss about the mode of heat transfer. Then we discuss about the uh, basics of thermodynamics, some thermodynamic principles that are required. So in this class we are going to discuss and derive the basic heat conduction equation. Okay, so the objective of our this lecture is that you should understand multidimensionality and time dependence of heat transfer and conditions under which heat transfer problem can be approximated as being one dimensional. Okay, so the first thing that we are going to discuss in this class, we are first going to derive the heat transfer equation in one dimension. Then we will obtain a differential equation of heat conduction in various coordinate system and simplify it for the steady one dimensional case. Okay, steady state one dimensional case heat conduction equation we will obtain. Okay, similarly we will identify the thermal conditions on surfaces and express them mathematically as the boundary and initial condition. So okay, so these are the objective of our present lecture, and we are going to discuss each one of them one by one. So in the last class, as let us recap from our last lecture. What we did in the last lecture, we discussed the meaning of conduction and wrote the basic equation of heat conduction, which is equal to Qx equal to minus Ka dt over dx. Then we discuss what is conduction. We defined conduction, and this is given by the conduction equation is written with the help of Newton's law of Coulomb. Similarly, we described what is radiation and how the heat conduction by the radiation is the doesn't require any medium for the transfer of heat, and it is given by the equation that is shown over here. Okay, so this is what we discussed in the last lecture. That was the introductory lecture of heat conduction. So of heat and mass transfer, where we introduce you to the subject of heat and mass transfer. Okay, and in that lecture we discussed all these things with you. So let us start our you can say our today's lecture. And in this lecture we are going to discuss derive one dimensional steady one dimensional heat conduction equation. Okay, so as we know that heat transfer and temperature are closely related. We have discussed in the last class that heat transfer is directly proportional to the temperature difference between the two bodies. Okay, but as we all know that they have two different nature. Okay, temperature has only magnitude. Okay, we can only define temperature in terms of some values. Okay, we can say whether temperature is increasing or decreasing, and quantify this temperature with the help of quantify the temperature with the using some scale like Fahrenheit scale, like Celsius scale, and most commonly used you can say SI scale is Kelvin scale. Okay, so temperature is basically a scalar quantity. Similarly, we work with we similarly when it comes to the heat transfer has two things. One is the quantity as well as the direction. Okay, when we say that some heat transfer is taking place, we also say that in which direction it is taking place. Okay, we mostly say that from this body to this body heat transfer has taken place. Okay, and we also tell the amount of heat transfer. Amount of heat transfer is obtained using the first law of thermodynamics, and direction is also described using some relation. Okay, so heat transfer has direction as well as magnitude, so it is a vector quantity. This is the one thing that you should remember, that heat transfer is a vector quantity and we work with a coordinate system and indicate direction with plus or minus sign. Okay, so when we describe the heat transfer, we not only describe the quantity but as well as the direction of the heat transfer also. Okay, so as you can see in this figure, figure number 2.1, heat transfer has the in this figure, this is the hot baked potato. There is a hot baked potato, and the temperature at the hot baked potato is 50 degrees Celsius. Okay, magnitude of the temperature at a point A, and similarly, since it is a higher temperature, though, so the some of the heat is you can say is transferred to the surrounding, and the rate with which the heat is being transferred, 80 watt per meter square. It means that on per meter square surface, 80 watt of the heat is lost to the atmosphere. Okay, so in this way, as you can see, the heat transfer rate from the this hot potato to the atmosphere is not only given with the quantity, but as well as it has been defined that some direction has also been described shown over here. Okay, so in the second figure, figure number figure 2, as you can see, this is the hot medium, this is the cold medium. So heat generally flows from the hot medium to the colder medium. Okay, so again here the direction has been described, and the heat transfer rate is shown here as 500 watt, 500 watt per you can say 500 watt means 500 joule per second. Similarly, the colder here, as you can see in the in the lower part of the figure, again the direction is shown as a reverse direction of flow. Okay, like when the situation has changed, and the situation has changed in such a way that the previously the colder medium becomes hot, and now the hot medium has become colder, so the direction of the flow of the flow will be reversed. So as you can see in from this figure, that heat transfer is a vector quantity and it has magnitude as well as the direction. So driving force for any form of heat transfer is the temperature or difference. Okay, if there is a temperature difference, then heat transfer will take place from between these two temperature, or I mean you can say when there is a temperature difference, then there is going to be some heat transfer between the two bodies. Okay, larger the temperature difference, larger the rate of heat transfer. The prime coordinate system, as we are going to derive our equation in all the three coordinate system. So we will derive our equation in rectangular coordinate system, cylindrical coordinate system, and spherical coordinate system. In rectangular coordinate system, the coordinates are defined as x, y, z, and t. T means here time. Okay, so similarly the positions in cylindrical coordinate system are defined by r, phi, and z, and time or t. Okay, so r, phi, z are the positional coordinate system, and t is the time. Okay, it describes the time. Similarly, in a spherical coordinate system, the position is defined with the help of r, phi, and theta angle, theta, and t as earlier, or t is the time. Okay, so these are the coordinate system on which we will derive our equation of conduction. So these are the various distances and angles involved when describing the location of a point in different type of coordinate system. Okay, the meaning of the x, y, z in rectangular coordinate system, as it has been explained over here. Similarly, the meaning of r, phi, and z is explained over here. Okay, and similarly, the meaning of r, theta, and phi is explained over here. Okay, as you can see, the position of point is described here with respect to two angles and one positional coordinate system. Okay. Okay, so now let us first understand what is the difference between steady state heat transfer and transient heat transfer. Okay, this is a very important concept that you should understand. Steady implies that there is no change with respect to time at any point within the medium. Okay, so for example, as you can see in this figure, that let's say at time equal to 2 p.m. At 2 p.m. The temperature of the surface were 15 degrees Celsius and 7 degrees Celsius. Okay, and heat transfer was Q1 between 15 degrees Celsius surface and 7 degrees Celsius surface. The heat transfer rate was Q1. After some time, let's say at 5 p.m., if the temperature remains 15 degrees Celsius and 7 degrees Celsius of both the surfaces, and the heat transfer rate is again measured and it was found to be same as 2 p.m. Heat transfer rate, then we will say that yes, there is steady state heat conduction. Okay, the transient implies the variation with time or time dependence. Okay, now transient means that something is varying with time and it is dependent on time. Okay, as the time will progress, the heat transfer rate will also changed will also change. In the special case of variation with time but not with position, the temperature of the medium changes uniformly with time. Such heat transfer are called the lumped system. Okay, as you can see in the figure number 2, figure B, after at 2 p.m., if the condition this was the condition, and 5 p.m. condition changed to this one, and heat transfer rate also changed. So this is basically time dependent heat transfer rate, and with time heat transfer changes. Okay, so this is called the transient heat transfer. So now let us discuss the multidimensional heat transfer. Okay, heat transfer are also classified as being one-dimensional, two-dimensional, and three-dimensional. Okay, just like steady and transient heat transfer, there is one more type of classification that is called based on the whether the heat transfer is one-dimensional or heat transfer is taking along two dimension, or major heat transfer is taking on the three dimension. Okay, so in most general case, heat transfer through a medium is three dimensional. However, some problem can be classified as two dimensional or one dimensional, depending on the relative magnitude of heat transfer rate in different direction and level of accuracy desired. Okay, one dimensional, if the heat transfer in the medium varies in one direction only, thus heat is transferred in one direction and the variation of temperature and thus heat transfer in other direction are negligible or zero. Okay, so you can say that heat transfer is only one dimensional if other two direction heat transfer is very small compared with the heat transfer in one direction. Okay, so that is why that problem can be simplified as one dimensional heat transfer, because only in that direction most of the heat transfer is taking place. Similarly, if let's say that only two along only two dimensions or only along two directions, the heat transfer has some you can say has some significance, and along the third direction heat transfer is almost zero or negligible. So in that kind of heat transfer is called the two dimensional heat transfer. If the temperature in a medium in some cases varies only in two primary direction, and the variation of temperature in the third direction, and thus the heat transfer in that direction is negligible. Okay, so this is the meaning of two-dimensional. Okay, the general case is three-dimensional heat transfer. Okay, but sometimes there are some cases where heat transfer mostly takes place along one direction, or we are or in, you can say, in other two directions heat transfer is negligible. Then in that case, that problem can be simplified into a one-dimensional problem. Similarly, if along one direction the heat transfer is negligible compared with two other direction, then that kind of heat transfer can be simplified as two-dimensional heat transfer. So as you can see in this figure, these are in this figure, with the help of these figure, heat transfer in you can say in two-dimensional and single dimension and two dimension has been described. Okay, in this first figure, as you can see that heat transfer along this direction. In the first figure number 2.5, the along vertical direction, you can see that heat transfer along vertical direction is negligible. Okay, the only heat transfer that is taking place along these two direction, along x direction and along y direction. This is the x direction and this is the y direction. Okay, along z direction, because the length of the bar is large compared with the other two dimension, so most of the heat transfer may take place along these two direction. Okay, that is why this problem, even though there may be some heat transfer along z direction also, but since this problem along z direction, the heat transfer rate is negligible, very less, so that is why this problem can be treated as two-dimensional heat transfer problem. Okay, now look at the this is the window, or you can say the shield of window shield of the of a house. Okay, now what happens that the house is warm. Okay, some many times houses are warm, and outside temperature is very less, especially if it is winter. So what will happen, that heat transfer will take place from the house to the surrounding. Okay, now heat transfer can take place along this direction, and along the perpendicular direction through the you can say window. Okay, through the window, or these two direction, this direction and this direction basically represents the heat transfer through the walls. Okay, but most of the heat transfer will take place through the window from this direction. Okay, through the window. Okay, if you have a window or some window is opened, so what will happen, that some most of the heat transfer will take along this direction. Okay, so this kind of problem can be treated as one dimensional problem. Okay, because from other two direction heat transfer is negligible. Okay, heat transfer is negligibly small, so we say that this problem can be treated as one-dimensional heat transfer problem. Then let us come to the Fourier's law of heat conduction. We have discussed this in lecture 1. So again we are discussing in order to move forward with our derivation of the heat transfer problem, the heat transfer equation. Okay, so the rate of heat transfer conduction through a medium in a specified direction, say in x direction, is expressed by Fourier's law of heat conduction. For one-dimensional heat conduction, the heat transfer rate is given like this: q, or conduction q dot dot means that we are expressing the heat transfer in terms of rate. Okay, as you can also identify with the unit. Okay, the unit of heat is joule. Okay, and the unit of heat transfer is joule per second or watt. Okay, so this is the difference between heat and heat transfer. Okay, heat transfer has the unit of watt. Okay, and it is given by Fourier's law of heat conduction, that is equal to minus Ka dt over dx. Okay, you can see here negative sign is given. Negative sign is given because the heat transfer takes place from higher temperature. General direction of heat transfer is from high temperature to the low temperature. Okay, so this dt over dx will always have a negative value. Okay, this dt over dx dx will always have a negative value, because of temperature difference is taken as final minus initial, and final temperature, or you can say the end temperature of the other end, where the heat is being transferred. Okay, so you can see dt over dx will always be negative, because final pressure will I mean lower first we will take lower pressure, then the higher temperature. Dt means lower minus higher. Here dt means lower minus higher, lower temperature minus higher temperature. Because why we are taking lower minus higher, lower first and higher later? Because heat is, this is the direction of heat flow. Okay, so this quantity here is taken as first, and it is taken later. So b the um, when b since q is a vector quantity, so what happens that the it is the quantity at the head minus quantity at the tail. Okay, so that is why this quantity dt over dx will always be a negative quantity, and due to this negativity, due to this the heat transfer will always come as negative. Okay, so it will appear that heat is being transferred in the reverse direction. So in order to satisfy the directionality, we have put the minus sign, so that the heat transfer always comes out to be positive. A proper direction can be described. Okay, so that is why heat is minus sign is introduced here, so that the negative sign that is coming from the dt over dx can be taken care of. Okay, so that is why this negative sign is there. Okay, heat is conducted in the direction of decreasing temperature, thus the heat temperature gradient is negative when heat is conducted in the positive direction. So heat transfer flux at a point P on the surface of the figure must be perpendicular to the surface. Okay, heat transfer, whatever heat transfer is being taken place, heat transfer flux, heat or the heat flux that is shown over written over here, means that the heat transfer taking place over per unit area of the surface. So that heat transfer, since it is a vector quantity, so we always take heat transfer flux as on the surface as the perpendicular to the surface, and it must point in the direction of decreasing temperature. Okay, as shown here in this figure, as you can see that the heat transfer vector will be always pointed towards the decreasing temperature, and if n is the normal to the isothermal surface at the point P, the rate of heat conduction at that point can be expressed by Fourier's law, like Q dot n equal to minus Ka del T over del x. This is the equation with which we can express our Fourier's law in a particular direction. And again, since it is a vector quantity, so that this can be vector quantity can be divided into three components, that is qx, qy and qz. Okay, so qx, I is the unit vector, j is the unit vector, and k is the unit vector. This is how you have seen in mathematics, in your mathematics classes, and you studied when you studied mathematics. This is how the vector were you can say divided into three components, along x-axis, along y-axis, and along z-axis. Okay, so again then along along x-axis, heat transfer is given as minus kx dt del t over del x, then ky del t over del y, and kx del t over del z. Okay, so along each axis, along x-axis, y-axis, and z-axis, this is how the heat is expressed. Okay, heat transfer is expressed. So the summary in today's lecture, we have discussed the Fourier's law of heat conduction in detail, and in this lecture we have this is the first lecture in which we have started our derivation on heat conduction equation using Fourier's law. Okay, in the next classes onwards, we will derive a full-fledged equation for the heat conduction Okay, so today we studied the heat conduction equation and basic heat conduction equation, and the conduction in a medium is said to be steady when the temperature does not vary with time, and unsteady or transient when it does. Okay, this is the meaning of heat conduction. This is the meaning of steady and unsteady heat conduction. Then heat conduction in a medium is said to be one dimensional when conduction is significant in one direction only and negligible in other two dimensions. It is said to be two dimensional when the conduction in the third dimension is negligible, and three dimensional when the conduction in all dimensions is negligible. Okay, so this is the summary of today's class. We have discussed and we started our derivation on the general heat conduction equation. We will derive in the next classes the general heat conduction equation. Here are review question for you so that you can practice at your home and try to answer these question. And how these questions, these are the question. Like first question is, how does how does transient heat transfer differ from the steady heat transfer? Okay, we have discussed in the lecture that what is the difference between transient something means that is something time dependent. Okay, transient means something that is time dependent. Okay, so same can be said about the heat transfer. Similarly, steady means that is not dependent on time. Okay, so if you are observing a point, let's say at time t equal to 1 second, and you have observed, let's say, for 120 seconds, and if the all the properties at that point have not changed, then we will say that yes, that point, that is a steady condition, that is not depending on time. Similarly, how does one dimensional heat transfer differ from two dimensional heat transfer? Okay, so you can give any example of how the one dimensional, what is one dimensional heat transfer, and how the problem is treated as two dimensional heat transfer. Okay, just like the example I gave you earlier in this class, you can also give your example, mm, mm, some other example in your answer. Okay, similarly, heat is heat transfer a vector or scalar quantity? Okay, so again, we have earlier discussed that it is a vector quantity, and we have justified it why it is a vector quantity, because it requires the direction as well as the quantity. Okay, anything that requires direction as well as quantity, that quantity is called the vector quantity. Okay, it is very simple, so you try to answer these questions in detail. So these are the references from where we have taken our material. Okay, you can refer to these books. Thank you for this lecture. In the next lecture, we will discuss a new topic. I mean, we will continue with this topic of heat conduction. Okay, thank you.